Okay. So yesterday I stated the main theorems that we will see in the course, an outline of the famous theorem of Green and Tao, a more detailed proof of the theorem of Green. And as I said, all of this goes back to Roth's theorem from 1953. So that is the theorem we will take up today. But I ended yesterday's lecture by detailing for you an example constructed by Berin, which from 1946, which goes in the opposite direction to Roth's theorem. Namely, it tells you a lower bound it tells you how far Roth's theorem can, in principle, go. At least conjecturally, one could think that this is as far as we can go. Though Roth's theorem itself, the current knowledge on Roth's theorem is far from what is given by Berin's example. Okay, this is the story so far. So we take up Roth's theorem, and let me state it for you again in the forms that we had. So this is the theorem of Roth from 1953. Let n greater than or equal to 1 be an integer, and a be a subset of 1 to n. If a does not contain non-trivial three-term APs, then the cardinality of A is less than n over some log n. So if it does not contain non-trivial three-term APs, then its cardinality is necessarily smaller, in fact of zero density asymptotically in the interval 1 to n. Okay, and to just recall that a three-term AP, x, y, z, say, okay, it should be a triple, so x, y, z is a triple satisfying x plus y equal to z and is called non-trivial if x, y, z are all distinct. Okay, so this is a three-term AP, and this is the statement. So there's the equivalent form of Roth's theorem. Yes, x plus z is 2. Yeah. Could just write it. X plus z is 2y. So an equivalent form. So equivalent form of Roth's theorem So if delta is positive and n is greater than exponential constant by delta, then any a contained in 1 to n with cardinality A greater than delta n contains a non-trivial 3-term AP. Right? And the transition from this to that, this is very easy. This to that, for example, you just have to put delta here, cancel the ends, and just change the log to an expression in delta, and you will get, meaning move the that side and change the n, write n in terms of delta, you get an exponential, double exponential constant delta. So both these forms are useful, but the form in which we will prove Roth's theorem will be a weaker form than this. We will only show that if it doesn't contain non-trivial APs, then cardinality A by n goes to 0. Okay? I mean, the largest of such sets, its cardinality by n goes to 0. But the method we give, starting from, meaning the ideas that are in the method that we give, developing on this, the modern technology on Roth's theorem develops on this. And the best results have actually come from subsequent developments by Kroot and Sisask and Bloom on the work of Kroot and Sisask, which is a small note in the proceedings of the AMS giving an alternate proof of Roth's theorem informed by the work of Green and subsequent development. So that's that. So now I need to introduce some more notation going forward. So let's say some notation. So let f be any map from Z to C. Then lambda f will count the number of arithmetic progressions with x plus z equal to y with weight f. F of z, okay, so x, y, z, whatever in z cube. So given any function from z to c, lambda f will count the total arithmetic, 3-term arithmetic progressions weighted by f. So f of x, f of y, f of z, x plus y. This sum here means that it's the sum over all triples which satisfy this condition. Okay? So note that lambda f includes the trivial solutions, trivial APs, 3-term APs as well. Okay, the sum here includes the trivial ones as well. If it's not, you'll get infinity, which is okay, but I will apply this only in the case when the support of f is finite and the sum is finite. Okay? Oh yeah, but you may not, it's a map to C, so okay. So I must add here that the support of f is finite. With finite support. Then, okay, so this is one thing. So in particular, if A is a subset of Z, then lambda f1a counts, so then lambda of 1a counts the number of, is the number of 3-term APs with all 3 terms contained in A, right? So then lambda 1A is the number of 3-term APs contained in A. We'll just denote this by, so we will write lambda A for lambda of 1A, just for simplicity, okay? Just introduce this. Now, if another thing which will naturally count the number of non-trivial solutions in A. So, analogously, one could define T of F or whatever, the thing that I would call T of A. So now, let T of A, if A is a subset, when A is a subset of Z, T of A is the sum x plus y, x plus z equal 2y. This time you put the condition x not equal to x, y, z distinct, and here you have 1a x, 1a y, 1a z. Where of course this 1 subscript a is the characteristic function of a, which is 1 if the z, or 1a is the function which is 1 if x belongs to a and 0 if x does not belong to a. It's the characteristic function. Okay? So I'm using the symbol TA to count the non-trivial 3-term arithmetic progressions. Okay? So people might object saying T should suggest trivial. You can criticize my notation, but you must remember it. It's up to you. Yeah, but I certainly must remember that T here stands for the non-trivial APs. That is one. Then the final notation, at least at this point, is for any integer n greater than or equal to 1, we set Rn to be equal to the supremum of all the cardinalities of subsets contained in 1 to n such that Ta is 0. Ta is 0. Okay? So what is Rn? It's the, thus Rn is the cardinality of any maximal subset of A with respect to the condition that it does not contain, not containing non-trivial 3-term APs. Okay, so Rn is this number which is the maximal size. So it's the supremum over all this thing. Oh, is the cardinality of any, yeah, maximal. So you could have several sets which are of the largest size, but they all have to have the same size, and that number is Rn. The main point is that if a subset of 1 to n has cardinality strictly bigger than Rn, then it has non-trivial 3-term APs. Okay, so that's what one needs to remember from this notation. Good. So now one has a simple property of Rn, So you have this proposition, which is a very simple proposition, is that this time I will use small letters rather than capital ones. Okay, Rn m is less than Rn plus Rm for all m and integers greater than or equal to 1. So it's a subadditive function on the, it's a subadditive arithmetic function. Huh? Left side R has a different form than the right side R. That's again just a quirk of my handwriting. So I can change it back if you like. Yeah. The font style has changed midway. Okay. It's a pity humans are not machines. So, okay, so now how do you prove this? It's a trivial proposition. So you take the interval 1 to n. So the proof, so you take, say, the interval 1 to m plus n, which is equal to 1 to m union m to m plus n. Now you have for any a contained in this 1 to m plus n, of course a of a intersection with this. So a cardinality of a is equal to a union 1 to m, a intersection 1 to m union a intersection m to m plus n, and if t of a is 0, that is a doesn't contain any non-trivial 3-term APs, then t of this is also 0, right? It can't contain, and t of this is also 0. And since APs are invariant under translation, you can translate this back so that you will conclude that if so you have that if t of a is 0, then t of a intersection 1m is 0, hence cardinality of a intersection 1m is less than r of m, and t of a intersection m to m plus n is also 0. This implies that t of a minus m intersection with 1n is 0, and this implies that cardinality of t of a minus m intersection n is less than r of n. So from this you see that cardinality of a intersection m to m plus n is less than r of n, and hence cardinality of a is less than r of m plus r of n. And now passing to the supremum, passing to sup over all a with ta 0, r of m plus n. Okay, so it's a trivial proposition. Now the conclusion from this subadditivity is a standard conclusion from subadditive functions which take positive values. Is a thing, a lemma that appears in many contexts called facets lemma. It's useful in many subjects in mathematics. And that tells you that the limit Rn by n exists. Okay? So, corollary to this corollary is limit n tends to infinity Rn by n exists. Okay? So, this is consequence, and the reason for that is let k greater than 1 be fixed, then for any n greater than equal to 1, write n equal qk plus L and apply the sub-additivity by the proposition we get R of n is less than or equal to q times R of k plus R of L, right? Because you can just substitute for n q times k plus L and repeatedly apply this inequality. Since q, k, L are all integers, positive integers, you will end up with this. Now you divide by n to write this is less than q rk by n plus this is r plus rl by n. Okay. Now this would be less than q rk by qk, since n is actually qk plus L, so this will bound it from above, plus rl by n. So you cancel here and you get Rn by n is less than Rk by k plus Rl by n. Now you let n tend to infinity. So if you take lim sup, hence lim sup n tend to infinity Rn by n is less than or equal to Rk by k plus RL by n, which goes to 0. Okay? And now you pass to lim inf on this. Passing to lim inf, you get that lim sup Rn by n is less than or equal to lim inf Rk by k, which implies that lim sup and lim inf are equal and the limit exists. Okay? So this is an absolutely standard deduction from subadditivity, has nothing to do with the definition of R except the fact that it's subadditive. It's valid for all subadditive positive valued functions on the integers. Okay? And it is a classical lemma that goes by the name of the Hungarian mathematician Facets. Okay? So this tells you that Rn by n has a limit, and the form of Roth's theorem we prove is that in fact this limit is 0. I mean, it would be extraordinarily surprising if this limit were not 0. I mean, that would be a new natural constant, the limit of Rn by n. Highly unlikely that it's anything but 0. So weak version of Roth's theorem is theorem limit n tends to infinity Rn by n is actually 0. Of course, the proof I'll give will actually show that the limit exists and it is 0. So this part of the of what I said is somewhat superfluous. But nevertheless, it's good to know that this much you can make out without having to make a deeper study of R. Just the fact that the limit exists is a simple proposition. So this is the form in which we will prove this. So this tells you that, okay, this is 0. Therefore, it will follow that if A has positive upper density, then A contains non-trivial arithmetic progressions. Okay, and in fact, you can also deduce that if you have A which is subset of 1 to n with some fixed proportion of the thing of the numbers integers from 1 to n, then A contains non-trivial 3-term APs. Now, in Roth's theorem itself and versions of it like this, immediately you can only say that A contains non-trivial 3-term APs. But one would like a statement which says that the number of such APs is in fact large. In fact, if you have A which is a subset of 1 to n and A has more than, say, a positive proportion, delta n elements, you would expect the number of arithmetic progressions to be of the order n square. Because arithmetic progression is one condition x plus z equal to y, you fix x and z, then y is fixed. So x and z you can choose in n ways, so roughly you would expect n square is the number. But this doesn't immediately follow from Roth's theorem, and in fact, one had to wait till 1959 when Varnamides gave a very nice combinatorial argument which allowed you to deduce from Roth's theorem the fact that in fact the number of 3-term APs in a set is large. Okay? Since I'm into reversing the historical order of everything, and in fact Kroot and Sisak do this, I will first prove Varnamides' theorem and deduce Roth theorem from this result. Okay, so let me state what is Varnamides' theorem. So here is the theorem of P Varnamides. I think, if I am not mistaken, this is the correct spelling of the name, from 1959 or so. Okay, so suppose that, so let n greater than 1, and suppose that, A is a subset of 1 to n, meaning the integers in 1 to n, with T of A is not 0. Then for all m 1 less than m less than n, we have a lower bound for TA, which is TA is greater than or equal to the cardinality of A by n minus R of m plus 1 by m, this times n square by m power 4 times m power 4. Okay, actually I've probably written it in I could have written it in a slightly better form by combining the 1 by 4 m power 4 here and putting this entire expression with this as the numerator and 4 m power 4 as denominator in a bracket, and then multiplying it with n square. That would be better because it would tell you that the number of 3-term APs, non-trivial ones, is of the order n square times something that comes, that falls inside this bracket. Okay, so this is Varnamides' theorem, and we will prove this theorem first. Okay, now the proof of this theorem will take a little while, say a few, probably even up to the end of the lecture maybe. And it depends on two standard combinatorial principles. I mean, again, I don't know if using the word standard is the right thing, but okay, well-known combinatorial principles. One is overcounting or amplification, and the other is to use the first moment to, okay, so let's come to this. So the first principle, so we'll leave this theorem here, and I'll now deal with the principle that goes in, which is overcounting. Okay, so overcounting or amplification. This is a simple combinatorial principle, and we will use that in this context. Okay, so what is this? What does this deal with? Suppose let X be a set and A a subset, and let's say F a family of subsets of X. So given A subset of X, we wish to count the number of elements of this family that are contained in A. Okay, we wish to count the number of F in this family F contained in A. In other words, we want to get a lower bound. In fact, we want to get a lower bound. We want to show that there are enough of them. So SA equal, say, F element of this family F, and F contained in A. We would like a lower bound for this quantity SA. It counts the number of F's in the family which are contained in A, and I'd like a lower bound. So we wish to find a lower bound for this, which, okay, so we will in fact require a lower bound. Now the principle is to introduce an auxiliary family B. Pardon? For S it has changed? Okay, yeah. So something going on here, yeah. So the principle of this amplification is to introduce an auxiliary family which you just choose depending on your ingenuity or your mood at that moment, and use that to amplify this sum. So the sum that you have here, you amplify it, and somehow, and then if you're clever or whatever, at that point it works, your idea, you will choose this family correctly, and you will actually be able to obtain a lower bound just because you've chosen the right auxiliary family. Now, coming back to this thing, what we want to count is the number of non-trivial 3-term APs, and what we will use as an auxiliary family is the set of m-term APs, where m is this thing from 1 to n. Okay, so it's that you overcount using these m-term APs. You put 3-term APs into m-term APs, and that's your auxiliary family. Okay, so let me go on with stating this thing as a small lemma. So, lemma is let B be a family of subsets of X such that okay, and L be a real number such that L is greater than summation 1 F, so B containing F, B element of this family B, uniformly for all F in F. Okay, so let me explain the notation here more carefully. The sum I have written is summation B containing F. B belongs to the family B1. So what this counts is, what this requires is that let's say B is a family of subsets of X and L is a real number such that for any F in the given family F, the number of B's that contain that F should be bounded by L uniformly for all F in F. Okay? You just take any family B, a beta, which satisfies this condition, so these two parameters, and we will use this auxiliary family to get a lower bound for SA. Okay? So how does one get a lower bound for SA from this information? So let's just write the sum and simply plug in what we have. So SA is the sum of F in F, so F contained in A, F belongs to this family F, 1. But 1 is greater than or equal to this divided by L. So this is greater than or equal to F contained in A, F in F, and summation B contains F. B belongs to this family B divided by L. Right? So this, because the assumption is that this bound is valid uniformly for all F in F. So here you're counting for, you're summing over the family F, elements of the family F, and you're counting which F's belong to A. For each such sum and F, you introduce this sum here divided by L because that's less than or equal to 1. Okay? And now you just interchange the summations. This is irresistible if you do analytic number theory. You have a double sum, you have to interchange it, whether it makes sense or not. So you just do it, and then you get so you interchange this summation and you will get this is greater than or equal to 1 by L. This time you sum over the B in B, B in B. And what is the condition? F must be contained in B and be contained in A. So that means F is contained in A intersection B. Okay? And therefore your sum here would be sum 1 of F contained in A intersection B, F varying over the family F. Okay? And you've divided by an L. But this is exactly what would be called S of A intersection B. This is exactly what one would call S of A intersection B. Okay, I didn't even give us the statement of the lemma. I didn't complete the statement of the lemma. So here, let B be a family of subsets and L be a real number satisfying this condition. Then the conclusion of the lemma, which is not stated yet, is that S of A is greater than or equal to 1 by L times the sum over B in B, S of A intersection B. So this is the conclusion of the lemma. Okay, so you introduce an auxiliary family and you amplify the sum defining SA to include more sums, and somehow because you do this averaging trick, you end up with something that you can count better. Of course, it depends very much on the choice of the auxiliary family in the given problem. Now, this is a trick that appears in a large number of contexts. It's not just specific to combinatorics. It appears in a number of situations, but we will restrict ourselves to this particular simple version of this trick. Now, what do we do? How do we apply this to this theorem? So first of all, let us note that the theorem itself is trivial if n and m are, if m is very large compared to n. So up to here, I have explained to you the device that I am going to use to prove this theorem. And now let me turn to the proof of this theorem itself. Okay, so here the proof of this theorem, which will be in a certain number of steps. First is that the theorem is trivial if n by 4, n square by 4 m power 4 is less than or equal to 1. Simply because TA is not 0, so TA is greater than or equal to 1, and this cardinality A by n is less than 1, so this expression times some number that is less than equal to 1 is going to be less than equal to 1 in any case, and therefore this assertion is obviously correct. Okay, that's the key role played by this condition TA is not 0. Okay, so that's that. Therefore we assume indeed that the opposite inequality is true, and that would mean that n is strictly bigger than 2 times m squared. Yeah, I mean, it's either it's negative or it's less than 1. If it's negative, anyway the inequality holds, otherwise it's less than equal to 1. So it's less than equal to, because a by n is a number that is less than 1. And this is a number that's less than 1. So, okay, and TA is always positive, it's a count. So it's greater than or equal to 1. Therefore, you may assume that n is bigger than 2m squared. Just keep this in mind, because at the end, when we choose a particular parameter, we will use the small fact that is there. Okay, now let us use this overcounting lemma, taking B to be the family of m-term arithmetic progressions with common difference less than or equal to a particular k, which we will fix at the end. So let B be the family of k of m term arithmetic progressions of common difference D less than or equal to K. Okay, so you must precede this by saying where K will be chosen later, or let K be an integer, K greater than or equal to 1 be an integer, and then you let this be the family of APs having M terms, okay, with common difference D less than or equal to K. So this is the family that we take, and if you apply now this overcounting principle, you see, so what should be the family F? F is the family of all three-term arithmetic progressions. So SA is exactly the number of TA. Okay, this SA that I have written here in the general lemma is exactly what we have called TA. So TA is this sum, the number of F contained in A, F in F, where this F is the family of three-term, the family of three-term APs. Okay, so pardon? Yeah, non-trivial, non-trivial. Yeah. So this is the thing, and you apply it, apply the lemma with this choice of beta, and then you get here M-term APs are inside 1 to n. Yeah, in 1 to n. Common difference D in 1 to n. So now, therefore, you have TA is greater than or equal to summation of B in B of T A intersection B. But you see that A intersection B is contained in a set of M elements. It's contained in B, which is an M-term AP. B, which is an M-term AP. AP. And arithmetic progression is just the image of 1 to the interval 1 to M under a homothéty, right? It's just you send x to ax plus d, and the image of 1 to M under this or a suitably defined homothéty is the arithmetic progression of M term. Okay? So, if you see, if cardinality of A intersection B is greater than R of M, if this is true, then T of A intersection B will be greater than or equal to 1. R of M, because A intersection B is a subset of an arithmetic progression of M terms, which is the image of the interval 1 to M under a homothéty. Under homothéties, the property of arithmetic progressions having a non-trivial APs doesn't change. Okay, so if A intersection B contains three-term APs, that will go back to the interval 1, I mean it will go back to its image, its pre-image in the interval 1 to M. Okay, so R of this A intersection B, I mean T of A intersection B, if it exceeds R of M, okay, because these numbers don't change under a homothéty, right? If you have an arithmetic progression, see, if you have a homothéty phi like this, which sends x to say some alpha x plus beta. What I'm saying is if alpha x plus beta, alpha y plus beta, and alpha z plus beta, if these three form an AP, if then so do x, y, and z, right? Simply because alpha x plus beta plus alpha z plus beta equals 2 times alpha y plus beta. Cancel the betas, cancel the alpha, and you will get x plus z is 2y. Okay? And conversely, if you had x plus z is 2y, you could start that relation and add back these alphas and betas, as long as, of course, as your alpha is not 0. Okay? So, therefore, you see, okay, so you see that if A intersection B is a subset of an M-term AP. So, it's a subset of an M-term AP, and R of an M-term AP is the same as that of R of M. The size of the biggest subset of an M-term AP not containing a 3-term arithmetic progression is the same as the size of a similar subset in 1 to M, because of the fact that an M-term AP is simply the image under a homothéty. Yeah? Huh? We'll come to the capital L in a moment, yeah. So we'll have to put in the capital L surely. I will tell you what the capital L is. Yes, surely the cardinal. Okay, so here this is the main point in the entire proof. So you would want to keep this in mind, that if yes, so to apply this thing, so you notice that if I just am rewriting this thing, if A is greater than R of M, then P of A intersection B is greater than or equal to 1, because B is an M-term AP. Okay, so you use this fact. And secondly, as she just pointed out, I have to tell you what is L. L is, given a 3-term AP, what is the number of elements of B that contain that 3-term AP. Right? I have to give a uniform bound for the number of M-term APs that contain a 3-term AP. Now you look at an M-term AP. If you're given a 3-term AP X, Y, Z, okay? If you can fix the position of X and Z within the M-term AP, then that M-term AP is determined completely, right? Because suppose X occupies the ith position and Z or say occupies the jth position, then by solving these two equations, you determine A and B completely, the common difference completely, and therefore the arithmetic progression is determined. So you have to own the number of M-term APs that contain a given 3-term AP does not exceed the number of choices of positions within 1 to M. In fact, if the first one if the last one is position in say M choices in the first, actually has only M minus 2. You can indeed refine this argument further, but since for our purpose nothing more will be required than just to say that therefore the number of M-term APs containing a given 3-term AP does not exceed M square. Okay? So it follows that L is less than or equal to M squared. This is a trivial bound. You can improve it slightly, you can be somewhat more careful, get say M squared up by 4 or so, but that's not going to be important to what we want. Okay? L is less than or equal to m square. So here is the key count. Therefore, just to say, you have this sum here, TA is bigger than or equal to 1 by m square times T of A intersection B, and by what we have said here, this will be bounded below by the cardinality of or the number of B's such that A intersection B is bigger than Rm in cardinality. So if you can bound the number of B's below, and then you would get a bound, substituting that into that, you will get a lower bound for TA. Now when you want to bound the number of sets, say A is fixed, you want to count the number of A intersection B's which satisfy a particular condition, one of the devices is to first bound the cardinality of the sum of the cardinalities of A intersection B over the entire family, and then separate out from that sum those that satisfy your condition and those that do not, and from that get a lower bound for the quantity you want. Okay, this is yet another standard thing. So first let's look at the cardinality of A intersection B, B in B. Okay, let's look at this. So this cardinality is equal to D less than or equal to K A in A, the sum over B in B, B in this family B of 1BA. So B varies over the family B, 1B, the characteristic function of B, A over A, and D less than or equal to K. Because the beta, the family that we were considering, consisted of all m-term arithmetic progressions with common difference less than or equal to K. Right? So to get a lower bound here, I need to show you and the method is to show you a subset of 1 to n which is contained in a lot of m-term APs, and then just count its intersection with A and say that the intersection with A is big. So at least you have so many m-term AP intersections. So how does one? Okay, so you consider the interval ID here, which for any D, let us consider for given D, consider ID, which is this interval, namely 1 to m minus 1 D and n minus m minus 1 D. Any A in ID is contained in exactly m APs of m terms, with common difference D. Why is that? You look at this interval. This interval is cooked up with a very specific purpose. It's the obvious choice here. You look at any A satisfying this. So A is between 1 plus m minus 1D and n minus m minus 1D. Now you're looking at the family of APs with m terms and fixed common difference D. Okay? So if you determine the first term of such an AP, the AP is determined. because its common difference is fixed, its number of terms is fixed. Now you take any A here, you can either start back and go by steps of length D backwards, and since A is bigger than this, you will still hit an M term AP and not leave the interval 1 to n. Because A plus M minus 1D is less than, 1 plus M minus 1D is less than E. So you can go back M terms and still remain within the interval 1 to n. You can go upwards M terms and still remain within the interval 1 to n because A is less than n minus 1, n minus M minus 1D. So any A in this interval sits in exactly M. It can occupy any of M, M positions in an M term AP. Okay? I have to stop, I guess. That's shining red at this point. Yeah. So, well, we'll continue from this point tomorrow. I should have actually finished it. Well, never mind. We can probably review the thing tomorrow in the beginning. And no, it's just a few steps from here. I don't know, but it's time, so I guess. And they record these things. So.